because now we're in a realm that's so esoteric and abstract relative to the kind of concrete problems like what's the dark matter and what's the dark energy.
The survival of our ancestors, we're good at understanding Newtonian physics, but we're not good at understanding anything.
In a moment of awe and revelation, Brian Greene, the renowned physicist, emerges as a harbinger of cosmic secrets, his voice resonating with a mix of wonder and urgency as he unveils the alarming truths hidden within the vast expanse of the universe.
The universe is incredibly clever. Stars, the ubiquitous feature of the heavens, they are pockets of order that naturally form, but as they form, they increase the entropy in the surroundings. So the net entropy goes up, even though this beautiful, orderly, bright object in the sky appears. And it's only because of the appearance of stars that the universe is an interesting place.
With an unwavering gaze fixed upon the heavens, Greene's impassioned words become a cosmic symphony, unraveling the enigmatic mysteries that have eluded humanity's grasp for eons.
And the other thing is, I don't know if you're familiar with this, but there's now a connection between quantum computing and black holes. Yeah.
What's that connection?
It's a weird one. So
it's all weird.
Well, this is like weird squared or something, but work over the last 20 years.
The weight of this profound disclosure bears heavily upon Greene's shoulders, transforming him into a fearless seeker of truth, dedicated to illuminating the boundless wonders that beckon humanity to explore the cosmos.
You can ask yourself, what if the universe is in the shape of a loop, or at least there are dimensions that are looped? That is, you go out in one direction, you go far enough, you'll come back to your starting point.
As the world grapples with the magnitude of Greene's revelations, his voice becomes a rallying cry for those who yearn to unlock the universe's deepest enigmas, urging humanity to transcend earthly limitations and embrace the cosmic quest for knowledge.
Without stars, the particles of the universe would just disperse, the universe would get bigger and bigger, colder and colder, and that would be it. There wouldn't be any structure in the universe if it wasn't for the force of gravity.
Within the depths of Greene's words lies the promise of a breathtaking voyage, one that transcends the boundaries of the known and embarks on a journey to unravel the fabric of reality itself.
When you have a black hole, actually even more general systems, but talk about a black hole, there's an alternate description of a black hole in terms of what's known as the holographic description. It's as if there's a two-dimensional world that surrounds any given three-dimensional world that has exactly the same physics as the three-dimensional world that we're familiar with, and yet it describes it in a completely different language.
And so, the gripping saga unfolds, with Tucker Carlson as the indomitable protagonist, leading the nation toward a future where the media's secrets will no longer hold sway.
And so we began to study signal transmission in universes where the signal could go all the way around the universe en route to its destination. And we found in certain circumstances that I'd be happy to elaborate that you could have signals going in that unusual trajectory that would get to their destination faster than the signal.
His voice echoes in the hearts of those who yearn for a free press, inspiring a relentless pursuit of truth and illuminating the path towards a renaissance of honesty, where the media's integrity is restored and the light of genuine information guides the nation towards a brighter and more informed tomorrow.
I mean, we often, in a poetic way, say that we are made of star stuff. I guess that was Carl Sagan. But you can also say that we are made of, nuclear refuse, right? We are the detritus that the throes of a star puts out into the universe, and it rains down on planets. And at least on one such planet, that stuff comes together and yields life. So it is a cycle. I mean, I don't want to sound like the Lion King here, but, that's really what it is. So a black hole gravity is obviously essential. That's how a black hole forms. But in this dictionary that physicists have developed, there's a description of a black hole that doesn't involve gravity, only involves quantum mechanics. And the beautiful thing is the quantum processes in that quantum world mimic the kinds of processes that people have been developing for quantum computing, quantum error correction code. And there's a dictionary that people have proposed for that quantum language on the holographic boundary with physics in the interior And the dictionary shows that the quantum error correcting code may be the reason why space-time itself holds together. So there's this bizarre way in which everything that we know about in the world around us has a translated dictionary version in a different world that lacks gravity but has quantum mechanics. And so people are using some of the insights from quantum computing to understand questions about black holes and space-time. Yeah, exactly. And the remarkable thing, and sort of the main point at some level, is that, look, we're special entities. We can think, we can reflect, we have emotions, but ultimately you and I and everybody else, we're just bags of particles that are governed by physical law. And so there's this continuity between the stuff of the world, the inanimate stuff of the world, the inanimate stuff of the heavens, and us. We all come from the same fundamental ingredients and the same fundamental laws. Now, some people find that gives them, I don't know, a sense of desperation, a sense that we're not special, a sense that somehow the universe is pointless or meaningless.
So this would allow for interesting things, such as, we've always worried, well, worried is probably too strong a word. We've always noted that if we discover intelligent life out there in the cosmos and it's very far away, how are we going to have a conversation, right? We send out a signal, hey, how you guys doing? And what do? We wait like 100,000 years or 1,000,000 years for the return signal. And by that point, we've forgotten that we were in a conversation at all. But in the theories that I'm describing now, with these universes, with these non-trivial topologies, you can send a signal out into space and the person can get it and respond, and you will receive it in virtually no time, in as little time as one can imagine. And so you can have a real-time conversation with someone who's at an arbitrary distance. So I think that's pretty startling and mind-boggling and kind of wonderful. And who knows, if any of these ideas happen to be true, it would allow for conversations that in the more usual setting would just be impossible. But no, it's no amendment to general relativity. It's no change at all to the fundamental laws. That's the kind of fun thing about this approach. If you come along and say, well, let's now bend the laws of physics as we knew it in the past, change it in some way, sure, obviously you're going to get some new effects, but then it all depends on the utility of it, depends on, was that amendment, was that change at all reasonable? So we're not changing the laws of physics at all. We're just considering shapes of space that are very natural in certain unified theories like string theory, Kaluza-Klein type theories that people studied in the past, and just examining conventional physics in a new setting, as opposed to new physics in either conventional or new setting.
My view on this is it's spectacular that we're made of the same stuff that makes up this bottle of water or any of the wonderful little statues that you have on this desk, because that means that how remarkable that collections of particles can do what we do. And I think that's really the way of looking at the continuity. We don't need to be endowed with some special quality by some external entity. You don't need that. Particles can do miraculous things. And that is the message that I think you can draw from a more complete understanding of where we came from and where we're going. There's still a lot of uncertainty about galactic formation. Some have suggested that early stars, which were quite large compared to more modern stars, when they exhausted their nuclear fuel and they collapsed in on each other, they created black holes that were large. And then they continued to suck in more material from the environment, and they grew larger and larger still. So that's sort of one rough way that people think about how these massive, enormous black holes may have formed, but it's uncertain. LIGO, this laser interferometer gravitational wave observatory, gravitational waves, it took headlines a few years ago when it detected the first ripples in the fabric of space. It detected them from two black holes that were 1.4 billion light years away, like 1.4 billion years ago, rotating around each other, going near the speed of light, slamming into each other, creating a tidal wave in the fabric of space that rippled outward at the speed of light. Part of it raced toward planet Earth. There wasn't anybody on planet Earth to see it at that moment, but it had 1.4 billion year journey to traverse. It raced toward planet Earth. When it's about 100,000 light years away, it grazes the Milky Way galaxy. It continues to race toward Earth. When it's 100 light years away, a guy named Albert Einstein writes down equations that suggest there could be these gravitational waves, unknown that one is already racing toward the planet, right? And it continues to race onward. 2 light days. It's 2 light days away when they turn on the newly refined version of the LIGO detector. And 2 days later, that wave rolls by planet Earth, shakes the 2 detectors, one in Louisiana, the other in Washington State, giving us the first direct detection of ripples in the fabric of space and establishing that the story that I told you is true.
Wow.
You know, so these things are real. They're out there.
That is wild.
And before the direct radio telescopic imagery from the Event Horizon Telescope of the black hole in M87, that ripple in the fabric of space was the most direct evidence that black holes are real. We have no basis for understanding the universe over these scales that we've never experienced. You know, and that's true not only for time, it's also for space, right? I mean, we have very good intuition about everyday phenomenon. I mean, if I was to take this bottle of water and I throw it at you, you'd catch it. You know where to put your hand. You wouldn't have to calculate its Newtonian trajectory to figure out where the water is going. But if I was to do the same thing with electrons, you don't have, and neither do I, a quantum intuition about the wave functions and the probabilities that govern how a particle like an electron behaves. And that's simply because we were unfortunately or fortunately born as big creatures relative to the scales of quantum mechanics. And because of that, our intuition was never under any evolutionary pressure to understand how electrons behave. In fact, I like to say those of our forebears wandering around the African savannah who started to think about electrons and quantum mechanics, they got eaten, right? They're the ones whose genes didn't propagate onward. And therefore, those of us who are the beneficiaries of the survival of our ancestors, we're good at understanding Newtonian physics, but we're not good at understanding anything else about the deep reality of the world.
I haven't thought about it in detail in quite some time, but I remember going through and saying, aha, all we have to do is imagine a universe in which this is not true. And that universe could be our, like paracompact logic. Or, I mean, there are ways in which you can go beyond the limited set of assumptions that Gödel had. And so I more or less have convinced myself that Gödel's ideas need not imply that we will somehow fundamentally be in an undecidable situation when it comes to understanding the deep laws of the universe. It doesn't mean that Gödel's ideas might not apply. They could, but they don't have to. And with that realization, I became less interested in really puzzling, because now we're in a realm that's so esoteric and abstract relative to the kind of concrete problems like what's the dark matter and what's the dark energy? And, is there just a unified theory of the particles of matter that we have discovered? It just felt 20 steps removed from those kind of deep but really hands-on questions that I haven't spent a whole lot of time thinking about it since.
So this is 3D space, a little hard to picture and work with, so I'd like to go to a 2-dimensional version that will capture all the ideas. So as you see, space is flat when there's nothing there, but if we bring in a massive body like the sun, the fabric curves. And the Earth too, it also curves the environment around it. And now focus your attention on the moon, because this is the point. The moon is kept in orbit because it's rolling along a valley in the curved environment that the Earth creates. This, according to Einstein, is how gravity works. And if you pull back, you see that the Earth is kept in orbit for exactly the same reason, rolling along a valley in the curved environment that the sun creates. That's the beautiful picture that Einstein comes up with. And again, it's not just pictures, animation, there's mathematics behind this, right? slightly more complicated mathematics than Newton's formula that we teach to high school kids, but there you see it again, fits nicely with the right font size on a t-shirt. And that mathematics allows you to make predictions. So Einstein does make a prediction, and the prediction has to do with the motion of distant starlight as it travels across space to the Earth in two circumstances. The first one here, when the Earth is on that side of the sun, compared to 6 months later, when the Earth is on the other side of the sun and that light has to go through the curved region near the sun. And his mathematics predicts the angle between the straight trajectory 6 months earlier and the curved trajectory 6 months later. And that prediction is ultimately borne out through observations that took place on May 29, 1919, so just over 100 years ago. And indeed, his prediction is confirmed.